Hello everyone, welcome to the course of logic synthesis and verification. So in this lecture we are going to discuss about essential prime implicants, and after that we'll just proceed towards the heuristic based approach, that is espresso based system. So just move towards the essential prime implicant. So we have already some idea about the essential prime implicant. So here in this case, essential prime implicants are those prime implicants which covers only ones within this system, okay, within which covers only the onset prime implicants, okay, of the system. So here we have taken one example, that f having some onset function 0 1 2 6 8 9 10 and then 14. So from the onset it is clear that it is an 4 variable function. So as we have clear cut idea about the k map, so we can put all these onset function within the 4 variable k map. So this is this cell based k map where all the that is position of the variables can be designated as m0, m1, m2 and m3, m4, m5, m6, m7 and then m8, m9, m10, 11, 12, 13, 14 and 15. So what we can do, we'll just put all the onset uh, implicants into this 4 variable k map, and this will be like this, okay. So we are just putting all these onset variables into all the designated position, that is 0 as it is present, so we will just write this particular position as a 1. Similarly for 1 also we'll put as a 1. As 3 is not present, so we will keep them as a vacant position, or we can put there as a 0. So in this way all the prime implicants, what we will do, we just put as a 1 here in this case. So here how we can that make the grouping of all these that is adjacent onset variables. So we just need to cover maximum variable, okay, with the minimum number of covers. We just need to cover maximum number of onset variable with the help of minimum number of cover. So what we can do, we can make this all the corners, okay, as one cover. So this is one, fine. Then as all these variables are present, so what we can do, we can proceed with another type of cover, is this one, okay. And the third one, it will be like this, okay. So here 2 variable and here 2 variable, as we know that k map can be fold, okay, and this particular row and this row can be adjacent after folding. So we can make a cover with this one as well as this one, okay. So now we just need to check whether this all the onset prime implicants has been covered or not, okay, and it is observed that yes, we have covered, okay, all this. But whether we have utilized the minimum number of cover to group all the onset, so that is the main question here. So if we are just making this 4 variable grouping here and here, okay, so grouping with the 4 corners are actually, it is a non-essential part, okay. So as we are making a cover with this 4 variable and this 4 variable, this is sufficient to cover all the onset positions. So and if we just make only the 4 corners to make the cover, then it is actually not required, okay, to cover all the onset. So these 4 corners are actually the non-essential implicants. So how we can write, again I just want to show you the first one, the 4 variable, this one, these are actually which position these are. This is actually 2, this is 6, this is 14, and this is 10. So in this way, this is an essential cover, obviously, because to make this particular onset positions, what we need to do, we just need to make the grouping of this onset positions. So this is exactly this implicant number 2 which is shown here. Okay, another one is obviously, okay, if we just make a group of all the 4 corners, automatically this particular onset positions are not covered with the help of 4, okay, corner grouping. So what we can do, we can go with this particular grouping of this variable. So here in this case, if we just check, this is position 0, this is position 1, this is position 8, and this is position 9. So 0, 1, 8, 9 is another essential implicant. But we have another possibility with the 4 corners, that is the 0, 2, 8, and 10. This is exactly non-essential to cover all the onset, okay, that is variable. So here in this case, this 0 to 8, 9 is the non-essential implicant. So it may possible that when some onset implicants are given, so all the covering are actually not required, okay, to group all the onset positions. So if the minimum number is covered, and in that case what happened, if we do in some other way, okay, where all the onset positions can be covered, then it is actually the essential implicants. And some that is a redundant covering, because this is actually the redundant covering, because already we have covered with this one, fine. So it is a non-essential implicants, fine. So if don't cares are used, so as I have already discussed that don't cares are actually those particular conditions which are exactly not occur during the application of the problem, okay. So these are exactly the incompletely specified function. Why incompletely? Because to make the onset covering, if some of the don't cares can be used, then automatically we can use those, okay, otherwise we'll just keep them, okay, as it is. So here in this case, what do we have, that is the output of the function is irrelevant for some input, okay. So the input might never occur, okay, and input is invalid. So in that case, actually the don't cares are represented within a function. The function is incompletely specified when the multiple completely specified functions can be implemented, okay, with the help of the don't care system. In case of K-map, we just designate or specify with the help of this cross, okay, for the don't cares. Here in this case, the output can be set to 1 or 0 based on our requirement. If some of the onset positions can be covered with the help of don't care, then we'll put those don't care as a 1, otherwise we will keep them as a 0. Then what we need to do, we just need to choose all those don't care positions judiciously, okay, in our convenient method, okay, in our convenient way. So what we need to do, we just have to do the maximum block size or maximum covering with the help of this don't care. Like some specifications of the don't care conditions are given like this. If some functions are given with the 4 variable, where variables are represented as a w, x, y, z, and our onset positions are given 1, 3, 7, 11, and the 15, and don't cares are also represented other than this onset positions, okay, which are comes under this offset condition. But what is the condition for the don't care? They are never occurred, or it may possible that this is a invalid conditions. So whenever it is invalid condition, or this condition will never happen or never occurred in future, so this is termed as a don't care. So 0 to 5, these are the other positions which can be used as a don't care, fine. So one example is shown with the help of don't care. So here in this case, f again the onset positions, as I have already shown, that 2, 3, 7, 11, 15. So this is exactly, it is the 2, 3, okay, then 7, this is 7, this is 11 position, this is 11, this is 15, this is 7, and this is 2, and this is the 3. So these are the positions. And what are the positions of the don't care? It is a 0 to 5. So this is the 0th position, okay. Then we have this is the second position, 2 position of the 2, and this is the 5th position. So here in this case, how we can make this grouping possible? So always what we have learned from our digital electronics, that maximum covering or maximum grouping can be given, that is the most preference is given to the 8 variable adjacent to each other than 4 variable. So here in this case, if we just forget about the don't cares, so we can make the grouping in this way, this one, okay, one group, and we can make a group of this one, fine. So there is a possibility if we just include the don't care, okay, if we just include the don't care. So here in this case, we can make a grouping with the help of these two don't cares, and covering with the 4 positions it is applicable. So if we just do this one, so the final variable that occur, that is equals to yz, okay, that is represented from here, and the covering with this, the variable that it will come as a w bar and the x bar, fine. Similarly, now question may arise whether there is any other realization possible. Yes, of course, okay. So all the possible realizations are correct, but we just need to choose judiciously based on our desired output, whether that gives us the best area or best power or best delay or best temperature, what, okay, particular direction we want to realize our circuit. So another realization is, yes, we can make a grouping with this 4 variable, and we can also make the grouping with this 4 variable. Here exactly we are using only one don't care, but we are using the 2 redundant variable. So here only one redundant variable is used, but here in this case we are using the 2 redundant variables. Now it is based on our requirement, again I just want to tell, okay. So here we can write it as a yz plus w bar and the z bar based on this 4 variable covering, okay. So this is how we can use the don't care, and we can set different types of realization, and it may possible that this particular realization and this particular realization may give us different numbers of that is the switching activities, which exactly gives us the idea about or estimate the power requirement of the circuit, okay. Later on we will see how this variable switching from its on state to the off state can gives us the value or estimate the power requirement, okay. So exactly the 2 level logic optimization, here in this case we can use the K-map based method, or we can go with the Quinn-McCluskey's based method. All this method already covered in digital electronics part that we have already studied, okay. I will not concentrate over these 2 particular types of methods, but what is our target? Our target is to how if the number of variables are getting increased. So here in this case, okay, how heuristic based method helps us to find out the near optimal solution. So what is near optimal solution? So this is a particular domain where exactly we are just trying to find out the optimum solution. So in one direction it is the fx, that is the function of x is there, and we just try to find out the value of x at a particular instant where the desired output can be observed. So here in this case it may possible that we are just start from at a particular instant, that means we are just start with some solution and we will perturb, okay. Perturb means some of the parameter we will just change, okay. Here how we are changing the parameters, that means we just try to cover the maximum number of on state, and we just check whether we are going in the right direction or not, our cost parameter or the function, okay, is getting reduced or not, okay, the fitness of this equation is getting reduced or not. Okay, so if we are just going in this direction, that means we can consider that yes, we are on the right path, and somehow, okay, if we are just going in the opposite direction, that means we may find that this is not the right way, so we can change our direction based on requirement. Okay, so just consider we are just going in this direction, so somehow, okay, we can reach the some minimum point. Okay, so exactly we don't know whether it is the ultimate minimum solution or not. Okay, so after more perturbation, okay, so more perturbation, that means we will just start with some solution. Okay, here we are just start with any solution, and this particular solution is just inserted with some perturbation. Okay, perturbation means we are changing some of the parameters and trying to get whether we are going towards the minimum solution or not. Okay, so after reaching this position, again if we are just going in this direction, that means we have to keep track about our minimum solution. So here in this case, when we start with this solution, okay, when we are just getting some minimum solution, okay, the final, I'm just writing here, final is one variable, so we just need to store the minimum solution within this. Okay, or we just keep track, or we just keep into the memory, okay, about our possible solution. Okay, so just consider after reaching this position, because when we are just coming to this one, automatically the solution is getting minimized. Okay, so as it is minimized, so we are just updating our final solution. Okay, so when we are just again perturb, and the curve is, the solution curve is going. Okay, so this is exactly the cost, or I can consider this is the fitness curve. Okay, if fitness curve it is going upward, that means we will just discard this value. Okay, as we have just store the minimum solution here. Okay, so whenever some worst case solution is obtained by perturbation, will not update, will keep it. Okay, so up to how much we will do this one? Okay, if we are satisfied with the solution, first of all, okay, the first, if we are satisfied, okay, if we are satisfied, the first one, or the second one, if it is a timed out. Okay, it is a timed out. What is that timed out? That means we have given some parameter that do it for maximum this much number of times. Okay, that is run the perturbation, okay, change the characteristics for at least 50 number of times, or 100 number of times, or it may be 1000 number of times. Okay, so if it is a timed out, automatically the best solution, as we have stored it, okay, we are just getting with this solution. Okay, or it may possible that if there is a no improvement in the fitness or the cost function, okay, so we are just come up with the best solution. Now what exactly the and this particular method is termed as a simulated annealing method. Okay, what is simulated annealing again? Okay, it is just a little bit of change. We are just, we have start from this direction. Okay, we have start with this direction, this particular position. Okay, position, and it is going in this direction. That means we are do the perturbation, and automatically the solution is giving us some better fitness. Okay, and if it is a better fitness, automatically we will reach to a particular minimized solution. Okay, so this is a minimum solution, and as we are just keeping the minimum solution into some variable. Okay, so obviously we'll keep track, okay, within the memory, that this is the some solution, but we don't know whether it is a minimum solution or not. But for this particular type of perturbation, this is the minimum solution. Now what the system will do? Okay, when it is just getting increased at a particular instant, again it will not, okay, continue the process. What it will do? It will just reduce, okay, reduce, and it will try to start from another point. Okay, it will try to start the process from another point. So this is the point I'm just considering. So now from this position, okay, now it is converged towards this one. Okay, so as it is converging, so as we can see that this is the minimum solution. Okay, this is the minimum solution. From here it is a g of x is getting some value. Okay, it is the g of x, I'm considering g of x dash. Okay, so this value is actually stored inside this value. So as we are just start from another solution, it is a solution number x I'm just considering. Okay, so we have started from here, and earlier that was solution y, just consider. So from solution number x, again it is just try to perturb, and we are getting some minimum solution. So the new solution will not accept till up to this position. Why? Because it is still g dash of x. Okay, so previously the minimum solution that actually we have, that is the better. So till up to this much position it will not accept. Okay, so when some solutions are getting here, automatically the new solution, that is the final is updated. Okay, finally is updated because we have reached up to another point. Okay, another point which is best. Okay, now again we will just try to move in this direction, and again we reach another minimum point beyond which there is a no reduction into the cost or the fitness function. Fine, so it will just update this minimum value into this final, okay, variable, where exactly we are just keeping track of what is the minimum position. Okay, so here in this case, how we will term this? Earlier that particular minimum position is actually the local minima. Okay, it is the local minima, and this is the global minima. Okay, this is global minima, means okay we are getting some better solution. Now okay, just consider that somehow, okay, we are not reach up to this position. Okay, and it is just going here to here again. So in this case, obviously this will termed as a global minima. Okay, if it will go like this, fine, because it is not reach up to the g bar of x. So this is exactly as we have started from one position and we try to converge, and after getting some minimum value, again we'll try from another point and try to converge the solution. Okay, so this type of methodology is termed as the simulated annealing method. Okay, so based on simulated annealing, actually the espresso is developed. It is a type of heuristic based on simulated annealing. Here in this case, we'll start from some initial cover. Okay, we'll start from some initial cover, and this may be the min term itself. Okay, so it is a min term itself. That means this is min term, all the min terms. If you just write, okay, f is equals to summation of m, if it is given 0 1 2. Okay, and it is a two variable. Obviously I can write x and y are the variable. So this 0 1 2 can be represented as a x bar y bar, plus 1 as represented as a x bar y, plus 2 is represented as a x y bar. So I can consider this as one solution. Okay, now from this solution I will try to converge towards the minimum solution. So initially, so we have some variable. Okay, I am just considering it is a final is one variable. So we'll just keep this particular min term positions and representation, this expression, as a final, and after that we'll just try to update it accordingly. Okay, whenever we are getting some better fitness or some better minimum value. Okay, so how we'll modify the cover? Make it prime or the e-redundant. Okay, so cover first. Okay, then we'll use three we means Espresso actually use the three different methods to minimize the cover. Okay, and it try to get the minimum solution. So here in this case it is a either it is a reduce, or it is a expand, or it is a e-redundant operations. Okay, so here in this case stop when no further improvement is possible, or it is a timed out. Okay, so no improvement is there or it is a timed out, we will just come out of the solution, and as we have already some minimum value stored here within this, so anywhere if you just stop you will get with some variable or some solution will be there. Fine. So what is expand? Make each cube as large as possible without covering a point in the offset. Okay, so with the help of all the cubes, we'll try to cover and we'll just leave the offset positions. Then it tries to expand and cubes in f. F means it is a function that is given with neighboring cubes. Okay, we'll just check the neighboring cubes whether it is present or not. If it is present, we'll try to make one cube with there. Okay, so with nodes in the don't care set if it is given, okay, or to form the large cube. So first of all, if neighboring it is an onset, we'll try to cube. If there is a don't care set also, we'll just try to make it a little large so that the number of literals will get decreased. Then it takes the essential subcubes and tries to expand them till they become the prime implicant. So what is our target? We'll expand till it is a prime implicant. That means further no more reduction is possible. That is exactly the prime subcubes. Okay, we'll just go up to the prime implicant. Next, each non-prime implicant is expand to a prime. Okay, again what it is, the non-prime implicants, okay, it is expanded and it will reduce up to how much? Okay, up to it is reached to the prime and it is replaced by a prime implicant that contains it. So within this, we just need to find out what are the different prime implicants, and what we'll do, we will just take only those prime implicants. Okay, so what is this exactly the expand method? This is a 3 variable hyperspace, so where all these bubbles are exactly the onset. Okay, these are the onset. So this is one onset, this is another onset, this is another onset, and this is on this. These are the onset. So here in this case, what our target is, we'll start from a particular instant, okay, particular onset, and try to find out whether there is a neighboring cube or not. So if we just start from this position, okay, and we are moving towards this direction, and we observe that yes, another onset is available, so we'll make one group here. So this is a group. Okay, so again we'll start from another prime implicant and we just move in this direction. Okay, and we observe that yes, there is another one, so we can make with this one. Now, okay, we can move in this direction, okay, and observe that no other that is neighboring onset is available, so it is not possible. But if we just move in this direction, yes, another onset is available. So this is exactly how all the cubes can be covered. Okay, so this is exactly the expand from a particular onset position. Okay, what our target is? Our target is to check whether the neighboring node, whether the onset is available or not. Okay, if onset is available, what we will do? We will just try to make one cube with the two onset. Okay, then what is the second method? That is the reduce. The cubes in the cover are reduced in size. Okay, after covering, we just try to reduce the cube. Okay, try to reduce the cube. That means we just try to take out the possible literal from there. Then each implicant is reduced to a smaller on, okay, that is contained in it. We will just as it is what method that we follow to reduce this one. Then reduce one, okay, and the remaining one are still cover in the onset. Then we just need to check whether this is still cover into the onset or not. If again it is cover, we just try to reduce more number of literals. Might exist another cover with fewer terms of fewer literal. Okay, so this allow the newly formed cubes to expand in a different direction. So from the reduced set, again we just try to move in another direction and try to check whether now, okay, another node can be accommodated with the cover or not. The new larger cube can possibly be obtained by exploring the new direction. So in this way, when we are just trying to reduce, and again we just try to make the cover with this one. So take one example in this direction. So again, as we have just expand and make a cube with this two variable neighboring nodes. Okay, then we just try to reduce. What we are just try to reduce, that this particular, okay, cover, we just, okay, leave this direction and we just try to move, and we just try to check whether this particular, these two variables are adjacent to each other or not, and whether on state is available or not. Yes, it is available. From here also, if we just try to move, and it will get, yes, another onset is available, so that means these four nodes are adjacent to each other. Now what we can do, we can just make a plane, okay, within this hyperspace which are neighbor to each other. So here in this case, if a particular plane is accepted, so automatically only a single literal is sufficient to express that particular, okay, covering. Okay, so this actually gives us a better solution. So this method is exactly what the reduce method is. So we just try to reduce some cover and try to move in another direction and check whether another cube is possible or not with the more number of covering. Okay, the next one, it is the irredundant. Okay, we'll go for the irredundant method. Already we have the idea that the irredundant, so throughout the redundant cubes we will check whether the irredundancy is possible or not from there. Okay, so what is the irredundant? Makes a cover minimal, okay, or the irredundant cover with the onset. In this case, the irredundant cover, no proper subset is also covered. So you can check from here how to do this one. So here, okay, this is one onset, this is another onset, so we are just making, yes, this is a cover. So here also one onset is present, so we can make with this one cover. As this is another neighboring onset with this one, so we can make another cover. Okay, and this is also onset, so we can make the cover. Fine. So now we just check which particular nodes or onset are actually the redundant to each other. Okay, so we can observe that yes, this is a redundant node, this is a redundant node. Okay, so we just try to remove all those redundant node. Okay, so if this and these are the redundant node, we'll just eliminate, okay, the covering which is possible with the help of this two particular onset. Okay, so here you can observe that this covering is just removed. So now, okay, as this is a redundant, both these terms are redundant, so this covering is redundant, so we just remove this one. So now we have with this cover, okay, this is the first cover I can consider, this is the second cover, and this is the third cover. Only these three cover is possible to cover this 5 onset position. So this is exactly, we'll find the redundant, we'll just try to remove all those redundant and we'll make it as a irredundant node. Okay, so as much possible, first of all. So what the Espresso algorithm is? Espresso will start from the original function. Okay, original function is given with the onset. Okay, onset. So what are the onsets? So that is the all the minterm positions. So what it says, so with expression with the true form. Okay, true form, and we just have to keep in mind about the offsets also. Okay, and offsets are also put it into another function that is equals to r, and don't cares are represented into the function d. Okay, now we just need to expand the original function, okay, in the direction of the onset by removing the offset. So this is, that's why we just need to track the offset, okay, and we just need to expand the onset. Okay, so the expand cubes against the offset, so that we just have to remove all the offset. That's why this offsets are also considered while considering the expand. That is, we just have to keep in mind that we must not include all these offset. What is next target? Next target is to, we just need to find the irredundant, okay, expansion, okay, with the help of the don't care condition also. So the function which is expanded, again we just try to check whether more expansion or more covering is possible with the help of the don't care or not. and obviously we have to go with the irredundant cubes. Okay, so we'll do this operation. Okay, so under this we'll start the again the reduce. Okay, reduce means the covering. Okay, with the onset we'll just try to reduce, we just try to minimize it, and then again we'll expand against the offset condition, and we'll find the irredundant expansion with the help of the don't cares. It is our target, because these don't cares are the incompletely specified locations which are exactly invalid or the not occurred. So we can consider this don't care for the irredundancy with the system, and obviously we'll do this operation, still we are getting a stable solution. So from here it may possible that we are getting some minimal or the minimum or the local minimum position. Okay, so we'll keep, and this value will be stored inside. Then we'll do again some perturbation. So how we'll do the perturbation? With the help of the reduced gasp. Okay, what is reduced gasp? Okay, I'll explain, but you just, it is another function. So now reduced gasp, that means we just remove some of the cover and we just try to, as I have already shown you, remember the perturbation. So here in this case simulated annealing, so we'll start from in this position from here and try to get some, okay, some minimum value. So now it may possible that we'll just reduce and try to start, and we just try to move in another direction so that the convergence is possible, okay, towards in another minimal position. So that can be possible with the help of reduced gasp. Reduced gasp is nothing but will add the cubes that can be reduced further. Okay, so expand again, okay, with the help of reduced gasp. Okay, expand the cube that covers another direction. Now what we'll do, we will just irredundant with the help of this function and this reduced gaps and with the help of this don't care. Okay, and we'll do this perturbation till we are not satisfied with the solution, or it is a timed out, or the cost function is not improved further. Okay, and finally we'll verify whether the particular function that what we received, that is correct or not. That is the verification with the input and the final output. Okay, so this is the Espresso algorithm. So here in this case it is very easy. Okay, it is very easy. Here we'll start with the original solution. We have to keep the offset and the don't care. We'll expand. Okay, and after that we'll try to find out the irredundant with the help of the don't care. Then we will just come inside some loop. What is this loop? Okay, we'll start reduction from a particular position and try to get some minimum value. Okay, so here we are getting some cost. Okay, we are cost or some fitness. Okay, I'm just writing this fitness. I have just normalized it and put the cost or fitness in a range of 0 to 1, just consider. And somehow if we just go in this direction and our fitness lie or fitness value is equals to 0.6, just consider 0.6, and as the minimum number of this value, that means more fit is our solution. So at a particular instant, okay, if we just go in this direction, our fitness value is equals to 0.6. Now what we'll do again, we'll just perturb it. Okay, and we'll do the more, we'll reduce and we just take another particular position and try to go in another direction. If we just go into another direction, automatically we may go another, okay, minimum solution where it may possible that our cost function is equals to 0.45. Okay, as I already told, the minimum number of cost is the better fitness. So in this case, okay, we'll just consider this and we'll update it when, okay, after perturbing it. Okay, what is this perturbation? That means we'll just reduce and try to start our that is observation. We'll try to start, or we just try to converge, okay, from another point and try to reduce the circuit. Okay, what we'll do, we'll just reduce and we'll expand and try to find out the irredundant solutions. Okay, so what is reduced gasp? Okay, so reduced gasp is nothing but it is the, for each cube of f, add those subcubes of the cube that are not covered by the other cubes. Okay, it uses don't care to ensure that new subcubes are not produced for just some don't care nodes. So this is the reduce. That means we will just go in one direction and just consider this is a one covering. Okay, so we'll just remove this covering, and if we have another neighboring element, so we just try to move in another direction. Okay, this is exactly we are just perturbed, so we are just moving in another direction. This is the reduced grasp actually. So again, how we will do the expand grasp? So expand subcubes and add them if they cover another cubes. Okay, later use e redundant, okay, to discard the redundancy. Okay, if there is a redundant cube, obviously we'll just remove all those redundant covering. Fine. Take some example for the reduced gaps and the expand gaps. So if we start from this position, okay, it is a 0 1 and we have possibility to go in two different direction. Okay, so here in this direction as well as in this direction. So we have another onset here, so we can make a grouping here, we can make a grouping here. Okay, so in this way we can just reduce the number of literals by covering the neighboring onset. So here in this case, what we'll do, we just try to go, okay, in the irredundant positions. Okay, so here if you just check, this particular node is actually the redundant because it cover for the both direction. Here also for this particular covering also it is covered, and for this direction also it is covered. That means it is a redundant. So we will check the irredundant positions. What are irredundant positions? This is exactly this one and this one. Okay, and we just try to move in different direction whether we are getting the more covers or not. From this particular position we can go in this direction as well as in this direction. Okay, so here also, okay, for this particular condition it may not possible, okay, to cover the position as it is a offset is available at 1 0 direction. From here also from 1 1 we can go in this direction as well as in this direction. So here in this case also, okay, one onset is available, so it can make a group in this way. Okay, but grouping of or the covering of in this side is not possible. So in this way what we will do, exactly the methodology is very easy. So we just try to cover from a particular point and try to find out what is the redundant point. We just remove our covering from that particular redundant position and will go the neighboring irredundant positions and try to reconstruct the covering. Okay, so this is exactly the reduced gaps. What is the expand? Expand is from this irredundant position we just try to make, okay, this covering. This is actually the expansion. Okay, expansion from this reduced gasp. So another example is shown, okay, for your better understanding. So x is equals to a bar b plus ab plus a bar b bar. So for this particular condition, okay, so this a bar b is this one, a bar b bar is this one, a b is this position. Okay, so how we can do the expand? By making the covering. So covering is possible in this way. Okay, this is the covering and this is the covering. So now we'll go with the irredundant positions. What are the irredundant positions? So we just need to find out what is the redundant. Redundant position is a bar b. Okay, this is the redundant position. So we just try to reduce the number of cube which comes under this particular a bar b. So here in this case the first reduce condition will just remove this particular node. If we just reduce this particular node, automatically what we will have? We'll have this particular covering and this particular node. Okay, then we will just expand again. So if we just expand again and we just try to move, okay, from this particular node, automatically, okay, we have two direction again. We can go in this direction, we can go in this direction only. So here in this case, as it is a offset, okay, so as it is a offset, so this covering of a b bar is not possible, but covering of a bar b bar and the a bar b is possible. So again, okay, we'll go in this direction. So again what we'll do, okay, here we have just reduced this particular covering. Now we have another option and we have to go to that particular option also. What is that option? That we'll keep this one and we'll start from another redundant node. Okay, so this is exactly this position. Okay, so here again we'll just skip this one, and from this particular node we'll just try to move. And what we observed? We observed that this is also can possible to move in this direction as well as in this direction, and as this particular onset is available, so it can make a covering with this one. So you can check, okay, for this particular condition these two are similar, so but we have checked all the possible condition. Okay, so this is a stable cost. Okay, so after verifying all the redundant that is the onset, okay, we just need to cover all the onset or not. Okay, we just need to go and verify, and we just come across the stable cost position. Okay, and then again we'll just pattern this one. So here again we'll start with it is another example. So we have some initial cover. This initial covers are with some it is a 3 variable. So here in this case this is a on state condition, this is another, this is another. Okay, 1 2 3 4 5 6. Okay, 6 on state. Okay, onsets are available. So we'll do the first reduce. So how will reduce? We just need to check, and we just need to remove some redundant positions. What are the redundant positions? So here in this case this is exactly the redundant one. So we'll just try to remove, okay, this cover. So here you can check, we have just removed this one. Okay, and from this we just try to move in different direction. Okay, so as we have possibility to go in this direction as well as in this direction, as it is a off state, so no covering possible. But if we just go in this direction, so here another covering possible. So with the help of this direction movement, okay, we can expand and we are exactly in the right direction, okay, with the minimum cover to cover all the onset. Okay, so here, okay, so it is the right direction for the reduce and again expand. So what are the essential and the redundant cube in this case? In this case, if you just check, this is one cover, this is another cover, this is another cover, and this is another cover. So, and these are my offset, and this is the don't care condition. So if we just check, as we have the don't care, okay, we just need to check, can we incorporate this don't care and make a whole plane a cover? Yes, it is possible. So in this direction one cover is possible, and this direction another cover is possible. So in this way, with the help of this don't care, what we can do, we just expand, okay, the essential redundant cubes, the prime implicant of the redundant cubes can be possible, okay, with the help of this don't care. Just come to the Espresso conclusion. The algorithm successfully generate the new covers until no further improvement is possible. Okay, and then produces near optimal solution. Okay, why near optimal solution? Because it does not guarantee us this is the best possible solution, but it guarantees us, yes, this is a best possible solution which is near optimal. Okay, near optimal, that means it is a probable optimal solution at any particular instant. Then we use actually the PLA based representation within the Espresso to minimize the function, where exactly the sub functions are in the multi-level logic realization. This helps us, okay, in case of PLA based realization, and it can improve a very large number of circuit, and in case of Espresso, that is a 10,000 literals at a time, it can be reduced. 100 numbers of input can be minimized with the help of Espresso, and 100 numbers maximum 100 output functions can be reduced. Less than 15 minutes, okay, with a high speed workstation, okay, is sufficient to reduce this maximum condition. Okay, thank you. This is the total algorithm which is used for the Espresso based heuristic system.